Compositions of functions. First, it's really important that you understand what a function is before we go into compositions of functions. So, a function is sort of like a tool that takes in a variable and does some operations to it, like multiplication, division, addition, subtraction, maybe the nth root, or something else. Each function has a name, like f, g, h. So here we've got 4 functions. Their names are f, g, h, and j. These functions also have variable names for the name of the variable being used. So actually, all of these functions have the same variable name. They're using a very common variable name, x. So this is f of x. Sometimes though, we want to set x equal to a certain number, so we can plug in or substitute this number in our function, like a function called f using a variable called x. So maybe you want to say x is equal to 7, or actually, maybe x is equal to 3. No. How about x is equal to 2? Or maybe x is equal to negative 999. Or to be more simple, let's just say x is equal to a number in the domain of f of x. Or to be even more general, maybe we're just going to plug in a certain something. So let's say x is equal to something, and that something is a cat. Well, let's plug in that cat into f of x. So wherever there was an x before, x is equal to a cat, so let's plug in a cat. So a very basic understanding of a composition of a function is plugging in one function into another function, like f of x. Different notations for compositions of functions. So let's look at this one notation. In this notation, it's made pretty clear that f of x is the outside function, and it's on the outside of g of x, which is the, you guessed it, inside function. This is read f of g of x. I think it's a little bit easier if I write it like this. F of g of x. So hopefully you can sort of see this layered thing like an onion. Another way to write the same thing is these two things. F of g of x and f of g of x are saying the same thing. They're just different notations. Notice this empty circle here. This is important. This is composition function notation. So don't confuse this with multiplication, the multiplication symbol. This dot that's filled in, this means multiplication. So, for example, 3 times 4 is equal to 12. But this is not what we're interested in. You can also have a composition of a function, but with a different function being used as inside function. So before g of x was our inside function, but now f of x in green is our inside function. So f of x is being plugged into g of x, the outside function. This is read g of f of x. G of f of x, and guess what? This is the same thing, g of f of x. And again, you can see that this empty circle is being used for composition function notation. Now let's find a composition of a function by ourselves. So here we've got two functions. One's called f of x and is equal to x squared plus 4, and we've got another function called g of x equal to the square root of x squared minus 2. So we're being asked to find f of g of x. This means we're plugging in g of x into f of x. So our first step is, let's just copy down the outside function. Well, what's the outside function? That would be f of x. You can see how it's sort of around g of x. Let's copy down f of x because, after all, we're going to have to plug in g of x. So we might as well know what we're plugging g of x into. So f of x is equal to x squared plus 4. Now, we're going to plug in, where there was an x before, we're going to plug in g of x. Okay, so before we had f of x, now we're going to have f of g of x. And before we had x squared, so let's make that g of x squared plus 4. Okay, but now let's substitute in the whole expression for g of x. Except actually, on this left side over here, I'm going to keep this written the way it is because this looks like composition function notation, so I'll actually leave the stuff on the left as it is. F of g of x, I'll just leave it the same way, f of g of x. But on the right side, let's plug in the expression for g of x. So g of x is equal to, what's that equal to? It's equal to the square root of x squared minus 2. Square root of x squared minus 2, oops, not 4, 2. And that's being squared. So this is g of x being squared plus 4. And let's simplify this. I'm actually going to switch colors just to show that we're pretty close to finding our final solution. So f of g of x is equal to, well, what is the square root of x squared minus 2 squared? That's just x squared minus 2, because we sort of did the opposite function, right? We're squaring, sorry, the opposite operation, we're squaring something that was already under a square root. So we just get x squared minus 2. But don't forget the plus 4 from before. Okay, so now let's find this, but simplify it even more. So f of x is equal to x squared plus 2. Final answer is f of g of x equals x squared plus 2. Now let's find a composition of a function that evaluated using a graph. So here we've got two graphs. Oh, let me just get rid of that. Now let's find compositions of functions that evaluated using graphs. So let's check out the problem we've been given. We've been given, well, let's remember how to read this, the outside function and the inside function and the variable name. So this is f of g of x evaluated when x equals 2, or you can read this as f of g of 2. Okay, so what's the inside function? Well, the inside function is g of x, but specifically g of x when x is equal to 2. So let's find that first. Let's find the inside function evaluated at the specific number 2. Okay, let's use this purple graph for g of x to help us out. So when x is equal to 2, what's g of x equal to? Well, that's 2. So g of 2, aka g of x when x equals 2, that's 2. So g of 2 equals 2. But we're not looking for g of 2. We're actually looking for f of g of 2. Well, now we know that g of 2 is equal to 2. So let's plug in g of 2. Well, f of g of 2 is f of 2. So this purple 2 is coming from when we evaluated g at x equals 2. Now let's evaluate f at 2. So on the graph of f of x, let's look at when x equals 2. This is, oh, we've got a hole. So because there's a hole in f of x at x equals 2, this means f of 2 is undefined. So our answer is going to be undefined. Again, how did we get this? Well, we evaluated our inner function at the specific x value, x equals 2. We found g of 2 is 2, then we plugged in 2 into the outer function f, and we found f of 2 is undefined because there's a hole in our graph.
Now let's look at finding the domain and range of the composition of functions. So in this case, we're finding f of g of x, so that would be plugging g of x into f of x. The function of f of x is 4 over x minus 2, so that would be 4 over x, and we're replacing it with g of x, so that would be x squared minus 2. So the first thing to do is to find the domain of the inside function, or in this case g of x. So for g of x, which is x squared, the domain would be all real numbers or negative infinity to positive infinity, because you can essentially square pretty much all numbers. For the range, squaring a positive number gives a positive result, and squaring a negative number also gives a positive output. So the range would be from 0 to infinity, and this includes 0, because squaring 0 gives an output of 0. Afterwards, you can move on to finding the domain of the composition. So for this function, which is 4 over x squared minus 2, you need to find out where x squared minus 2 is equal to 0, because that cannot be in the domain since you can't divide by 0. So you do that just by simply setting x squared minus 2 equal to 0. And then you just solve algebraically, and you get that x is equal to plus or minus radical 2. And make sure you remember the plus or minus, because squaring both of them can give a result of 2. So then these two are places, and they're not in the domain. So since the domain of the original function is negative infinity to positive infinity, these are the only places where the function cannot go, and it's not in the domain. So that would be negative infinity to our first place where the domain or the function can go, which is negative radical 2, union negative radical 2 to positive radical 2, and finally radical 2 to positive infinity. For the range, you can solve this by finding the domain of the inverse. So that'd be y squared minus 2 is equal to 4 over x, and y squared equals to 4x plus 2, and then finally y is equal to the radical. Then this value under the radical needs to be greater than or equal to 0, because you can't take the square root of negative numbers. So then you would set 4 over x plus 2 has to be greater than or equal to 0. Then you just solve algebraically. So then the range ends up being negative infinity to negative 2, and then from 0 to infinity. And this is taking into this, x has to be less than or equal to negative 2, so that should be a bracket, and then taking into the original range of the of g of x into account, so that'd be 0 to infinity. So now for evaluating with numbers, we're finding f of g of 5. So the first thing to do would be to find the value of g of 5, and then afterwards plug that value into the function of f of x. So for g of 5, the function of g of x was x squared, so that'd be 5, which is x squared, and that'd give us 25. Afterwards, we would plug it into the function of f of x, and then f of g of 5 is also equal to f of 25, because that's equal to g of 5. So then the function of f is 4 over x, which in this case would be 25 minus 2. So then that would give us 4 over 23 as our final